in and continue covering the lymphatic system. So we left off on this slide. We're talking about the primary leukocytes. Those are the blood cells. This is review from last unit. But you know what? Review is nice. We have the 5 leukocytes being neutrophils, eosinophils, basophils, monocytes, and lymphocytes. We aren't going to spend a lot of time on you knowing the relative predominance or how relatively abundant those leukocytes are. But as we look at these leukocytes, in this unit, we're going to focus primarily on what they do. That, since we're in the immune system unit. And we're going to dedicate a lot of time about talking about the most common ones, the neutrophils, and in particular the lymphocytes. We spend a lot of time talking about our lymphocytes. So, just to reiterate, neutrophils are the most abundant leukocyte. They're a granule site, so they have some granules in them. And when we think of neutrophils, they are, for lack of a better term, the first responders in our bodies. These neutrophils are constantly patrolling our bodies. They're moving through the bloodstream, they're moving through the tissues, and because they're constantly on patrol and there's such high concentration of neutrophils, they're able to get to the site of infection right away. And when these neutrophils get to the site of infection, for lack of a better term, they're kind of like kamikaze pilots from World War II. They'll try to phagocytize the bacteria or the pathogen, but a lot of times what these neutrophils do is they will release digestive enzymes into the extracellular environment. And when they release these digestive enzymes to the extracellular environment, these enzymes will destroy the bacterium and will also destroy the neutrophil in the process. So the neutrophils will kill themselves in the process of killing the bacterium. This process of releasing digestive enzymes has a very specific name. It's known as a respiratory burst. And that's the terminology that describes of these highly oxidative chemicals, or these highly electronegative chemicals. So when we think of the oxidative burst, it gets that, or the respiratory burst, it gets that name, respiratory burst, because our body will harness waste products from cellular respiration, in particular oxides and superoxides that are waste products transport chain, and use those waste products to make bleach, intracellular bleach, or hypochlorite ions. And then those hypochlorite ions are stored in a granule, stored inside of a storage vesicle, and then during the respiratory burst, the cell will exocytize bleach, or the hypochlorite ions, and kill the bacterium and kill themselves at the same time. We also have eosinophils. Eosinophils are characterized by having pinkish red or dark pink or light pink, depending on the staining of the eosin and how efficacious that eosin was. They'll be the pink granulocytes. And when we think of eosinophils, last unit, when we were talking about them, I really emphasized how they guard against parasites. And I'm going to strongly emphasize that again. That's something that makes the eosinophils really stand alone. When I taught a medical microbiome, we had a lab activity where we harvested blood from individuals and then did right staining on their blood in lab. And it was really hard for us to find eosinophils. But I had this colleague who had a persistent parasitic infection in his body, and I would always, hey, Jim, come over, I need to bleed you again. And we'd always harvest his blood for a lab because he had an elevated eosinophil count because of persistent parasitic infection within his body. But when we look at our eosinophils, they do more than just reduce the parasites in our bodies. They're these multicellular parasites. They're also going to help us regulate allergic responses. And this is the thing that's not as emphasized by our eosinophils, or not as emphasized by most instructors when they talk about eosinophils. Our basophils upregulate allergic responses. The eosinophils help to downregulate allergic responses. So if it's that time of year where there's lots of tree pollen or maybe mold in the atmosphere, if there's that allergen that person's allergic to, a lot of times that person will have a slightly elevated eosinophil in response to the overactive basophils causing them to have an allergic response. Our basophils are going to help us phagocytize antigen antibodies. We haven't gotten to that yet, but just to briefly talk about it, our basophils are sites. They can phagocytize pathogens in our bodies. And they are they're not very effective phagocytes. When we think of phagocytes, we think of macrophages, antigen-presenting dendritic cells that we talked about Tuesday. But eosinophils can phagocytize pathogens, but they're going to phagocytize a pathogen that's been covered with antibodies. I like to think of the eosinophil as my 5-year-old son. They're picky eaters. They don't want to phagocytize just any bacterial cell. They're going to be kind of picky and only eat the bacterial cells that have antibodies on their surface. Or as I like to think of them, a preference for sprinkled covered donuts as opposed to regular donuts. When we think of our basophils are the rarest of the leukocytes. They have lots of granules that stain dark purple, so they oftentimes are going to look like a large purple blob with kind of some speckles in them. And when we think of our basophils, I want you to think of modulating our allergic responses. So when we think of basophils, they are histamine, and the histamine is a double-edged sword. A little bit of something can be good, too much of something can be bad. And that's a good rule of thumb for all chemical compounds. Oftentimes when I taught medical macro, I would have students ask, oh, is this bad for you? Is this toxic? Or is this good for you? And I would have a wishy-washy answer. The wishy-washy answer is, it depends on the dosage and concentration. So when we look at histamine as a chemical compound, if we have just a little bit, it can be beneficial to us. It can cause vasodilation, it can increase blood flow, and cause more neutrophils to arrive at the site of infection. So just a little bit of histamine, hey, that's good. However, too much histamine doesn't give you a beneficial inflammation. Instead, you have an out-of-control allergic response when there's too much histamine. So when we look at our basophils, sometimes they are behaving appropriately and they release a little bit of histamine. Other times, in the cases of allergies, they release too much histamine in response to an inappropriate stimulus. As part of this allergic response and increasing the flow of blood, basophils are also going to release a chemical heparin. So in addition to making the blood vessels wider with the histamine, the heparin is going to make it less likely for the blood to clot, so that it makes it easier for the neutrophils to get to the site of infection. And speaking of neutrophils, these basophils need to sound the alarm. And they sound the alarm by releasing a chemical signal known as a leukotriene. So there's 3 primary chemicals I want you to associate with the basophils. The leukotriene recruit other leukocytes. The histamine promotes vasodilation, and then the heparin inhibits clot formation. All 3 of these chemicals work together in order to maximize the number of neutrophils and eosinophils that can arrive at the site of infection. And then when we look at the basophils, they can be transformed into mast cells, which chemically and structurally and functionally are very similar to a basophil. And then we have the lymphocytes. And this is the one that we're going to spend pretty much all of the week. Lymphocytes. There's a lot going on with the lymphocytes. Lymphocytes are the second most common kind of leukocyte in our bodies. And these lymphocytes can be broken up into 3 categories. We have the T lymphocytes, or T cells, that become immunocompetent in the thymus. We have the B lymphocytes that become immunocompetent in the red bone marrow. And then we have some of the lymphocytes that are turned into natural killer cells. And as we look at these lymphocytes, Some of these lymphocytes are going to be associated with exclusively the adaptive immune system. That's the third line of defense. Some of these lymphocytes will be associated with the second line of defense, our generic innate immune system that's inside of our body, the internal nonspecific immune system. One of the very different cell types, second line of defense, our internal generalized line of defense, to the third line of defense, our internal specific line of defense, is the helper T cells. These helper T cells, you can think of these as kind of like the quarterback immune system. They help to tell all the other leukocytes what to do. They can upregulate leukocytes, and they can downregulate leukocytes. The helper T cells are an important linchpin between the nonspecific and the specific immune response. We also have monocytes. When we look at our monocytes and macrophages, a monocyte, when activated, turns into a macrophage. So the monocyte is the largest of our leukocytes. It's also not very common. And as we look at our monocytes, when they are activated and turn into those macrophages, some of those macrophages are going to be actively patrolling the body, phagocytizing pathogens. And when we think of the monocytes and macrophages, they are a large, phagocytically active and presenting cell. They swallow pathogens, chop them up, and then show other cells of the immune system bits and pieces of the pathogens that they phagocytized. When we look at the wandering macrophages, these wandering macrophages are going to be actively seeking out pathogens, and they're going to be associated with connective tissue that doesn't have a lot of cellular matrix, so loose connective tissues. When we think of the loose connective tissues, you can think of the areolar tissues. Those are the two biggest loose connective tissues that these are going to be associated with. Those dense connective tissues, think of cartilage or compact bone, or maybe dense regular connective tendons and ligaments. Because there's so many extracellular matrix, those connective tissues, you don't have a lot of macrophages. It's hard for macrophages to move through cellular matrix. We have Halloween coming up, and if you're looking for a movie to watch, you should watch the 1950s version, not the 1980s, 1950s version of The Blob, where somebody has a genetic mutation and one of their macrophages grows out of control and swallows the town. It's hilarious. We also have fixed macrophages. And when we think of fixed macrophages, these are macrophages that are stuck in an organ. So fixed macrophages don't move around. And depending on the organ that they're stuck in, they're going to for instance, within our central nervous system, we have some leukocytes associated with that, the microglia, one of the glial cells we talked about last semester. The microglia are macrophages of the central nervous system. We have alveolar macrophages, which are going to be the primary way that we remove dust and pathogens from the alveoli of our lungs. And I believe on the bottom corner of this slide that was cut off, it said hepatic macrophages. But if you're old school and crusty, you're taught Knupfer cells, because that's the name of the guy who initially discovered them. And we'll also have macrophages in the liver that hang out in the liver only, those hepatic macrophages that help to remove toxins and large molecules that have been absorbed within the hepatic portal system. We also have a lot of proteins in our body that help to kill bacteria and viruses as well. It's worth emphasizing right now that antimicrobial proteins are currently a pretty area of research. Major pharmaceutical companies in the world have stopped researching antibiotics. There's just been no new developments, no promising fields of research in the last 2 decades for antibiotic development, and they millions of dollars into these research, or excuse me, billions into these research projects and getting no return on their investment. So it was actually 2 years ago that the last pharmaceutical company ended the last program in the world. Now we're looking at other alternatives to kill bacteria in our bodies, one of which is anti-protein development. Grow and purify these antimicrobial proteins and inject them into a patient. I know this isn't a microbiome class, but it's worth emphasizing because it just looks cool. We can also have bacterial designing viruses specifically that target focused on phage therapy, but they didn't have enough funding, and the research kind of fell off. But there's a lot more renewed interest in designing viruses to destroy bacteria as well, in addition to antimicrobial protein research. Now, for us in this class, we're going to focus on two antimicrobial proteins, the interferons and the complement system. And they're two proteins that help to destroy pathogens in two very different ways. So first, let's focus on the interferons. In case you're wondering, no, I don't want you to memorize this flow chart on the diagram. I mostly included this so that you could see how a virus gets into the cell. When that virus enters the cell, the interferon genes are activated. The infected cell starts to make interferons, abbreviated as an INF. The infected cell releases interferons, and the next door neighbor receives the warning sign. So when we think of an interferon, it's an altruistic way for a cell to respond to an intracellular pathogen. Most commonly, it's going to be a viral pathogen. And I say it's an altruistic way for that specific cell because there's no benefit to that specific cell. When a cell becomes infected with an intracellular pathogen, these interferons in no way help to fight off the pathogen inside of the cell that's making the interferon. But what the interferons do is they alert the next door neighbors. They help put the neighboring cells in that tissue on high alert and give those neighboring cells temporary immunity to some aspects of that pathogen. So when we look at the interferon cascade in that process, once that alerted cell has received an interferon from the infected cell, the neighboring cell is able to better respond to viral infection. In particular, once that viral infection gets into the neighboring cell, if it gets into the neighboring cell, that neighboring cell is better equipped to chop up the viral DNA or RNA and keep the virus from reproducing. Another way that interferons help the neighboring cells is that it's also going to activate natural killer cells and macrophages so that the infected original cell will be destroyed quicker and be less likely to send more viruses to attack the neighboring cell. As we look at activated natural killer cells, they are also, when activated, going to destroy malignant cells. When we think of malignant cells, these are cells that are reproducing out of control. A lot of our cells will start to reproduce out of control in response to a viral infection. There's a common vaccine. It hit the market, I want to say, in about 2002, 2003, the early 2000s. Gardasil hit the market. And Gardasil is a particular vaccine that vaccinates against the most common strains of the human papillomavirus. That virus has been associated with most cases of cervical cancer. And it's actually remarkably effective. It's been found that if you keep somebody from getting infected with these strains of the human papillomavirus, their cervical epithelial cells can't be mutated by those viruses, and then they don't reproduce out of control. They don't become malignant or cancerous. It's also worth emphasizing that reprogramming natural killer cells to target tumors and malignancies is a current anti-cancer area of research. So those are the interferons, the warning system for the neighboring cells. When we think of the complement system is much more targeted. Instead of sounding the alarm and alerting the neighbors, our complement system is going to focus on destroying the pathogen. Another way to really generalize the differences between the complement system and the interferon system is the interferon system focuses on intracellular pathogens, so either viruses or intracellular bacterium. The complement cascade is going to focus on extracellular pathogens. So it's going to focus primarily on bacteria that are outside of the cells. When we look at the proteins of the complement system, there's a whole bunch of proteins in the system, and there's no way we're going to cover them all in this short amount of time we have for the immune system. So just know there's lots of proteins circulating in our blood plasma, and these proteins can interact with each other to target and destroy bacteria in our bloodstream. So as we look at the complement cascade, or the complement system, there's four different ways or four different effects that they have on our bodies, and three different ways we can activate them. Our four effects that they can have are inflammation, immune clearance, phagocytosis, and cytolysis. And we'll talk about each of those four effects in a little bit more detail. In terms of the route of complement activation, I was really on the fence about including these in our presentation. We just didn't have enough time in this semester to talk about the three routes of activation. So know that there's three different ways we can activate the complement cascade. We're not going to talk about the specific details of those three pathways. Just know there's three different ways: the classical, the alternative, and the lectin pathways. But let's talk about what that complement cascade does. Once it's activated, it can cause inflammation. And as we look at inflammation, that inflammatory response is going to stimulate the mast cells and the basophils to release more histamine. That's going to trigger vasodilation. It's going to help to promote blood flow. And as we have more blood flow to that area, we're going to have more neutrophils and eosinophils arriving. So we can think of the complement cascade as the part of the immune system that activates the basophils, so the basophils can then call for reinforcements and have more neutrophils arrive at the scene of infection. We also find that during this inflammatory response, pathogen destruction is accelerated, primarily because the pathogens are exposed to more and more neutrophils. If we have more neutrophils arriving to the site of infection, that pathogen will be destroyed faster, either through phagocytosis or through the sacrificial respiratory burst. Another way that our complement system helps to destroy pathogens is through a process known as immune clearance. One of the proteins, we have complement protein number 3A and complement protein 3B. So just when we look at these abbreviations, just think one of the proteins of the complement system. And there are many different proteins of the complement system. If the complement protein 3B binds to an antigen-antibody complex, where an antibody is stuck itself to an antigen, it's going to bind to that complex and cause those red blood cells that are exposed to circulate throughout the liver and spleen. And within the liver and spleen, we have fixed macrophages that detect those antigen-antibody complexes on the erythrocytes, and then that allows for activation of our adaptive or specific immune system. We also have phagocytosis. When a bacterial protein or bacterial cell has a bunch of complement proteins on its cell membrane or cell surface, cell wall, depending if it's gram-negative or gram-positive, that bacterial protein, bacterial cell is going to be flagged for phagocytosis. So when these complement proteins bind to the surface of the bacterium, that bacterium is having a bullseye painted on its back, or a glowing neon sign that says, hey, you should phagocytize me. It's a similar response to putting antibodies on the surface of bacteria. Covering a bacterium with antibodies or covering a bacterium with the complement proteins allows for them to be targeted preferentially for for phagocytosis. And then probably my single favorite method that the complement cascade destroys bacterial cells is it turns bacterial cells into wiffle balls. And when I say turn them into wiffle balls, I mean that it takes the cell wall and cell membrane of the bacterium and it causes it to have lots of holes punched into it. It perforates the outer lining of the bacterium so that the cytoplasm of the bacterial cell spills out into the extracellular fluid. It loses all of its chemical gradients and loses homeostasis and dies. And this cytolysis, this process of causing the cell to self-destruct, happens when complement proteins bind to each other. So don't focus on specific names of these specific complement proteins. Instead, I want you to internalize this as a bunch of the complement proteins self-assemble. And as these complement proteins are self-assembling on the surface of the cell, they're going to form pores. Pores, holes that spontaneously self-assemble on the bacterial cell, are called a membrane attack complex, or MAC for the abbreviation. And as this bacterial cell has more and more membrane attack complexes forming on its surface, it has more and more holes punched in its cell membrane and cell wall, and it loses the ability to maintain homeostasis and kicks the bucket. This is a good summary slide talking about those 4 responses. I'm going to skip over this since we just had 2 slides on this, but I liked this and I want to include this part of your figure from your textbook because it summarizes the steps of inflammation, immune clearance, phagocytosis, and cytolysis. All right, let's have a review question. This is a fill blank. So the formatting looks kind of ugly, but blank are signals, that's a typo on my part, blank are signals produced by virally infected cells that alert neighboring cells to infection. So what's something we talked about that focuses on an intracellular infection, alerting neighboring cells to infection? And type in the word. Hopefully it's working for you. Let's go with 15 more seconds. If you haven't submitted an answer, please make sure you submit an answer. Five, four, three, two, one. Interferons, excellent. So we nailed it. The singular would work too. So interferons are those signaling molecules. Let's talk about natural killer cells. As we look at our natural killer cells, guys, gals, these are going to be cells that specialize in linking some components of non-specific to the specific immune system. These natural killer cells are a kind of leukocyte within our bodies that are constantly patrolling and checking to see what belongs and what doesn't belong. Some of you may have had a chance to ride a train for fun. And it's mostly just novelty at this point, but when you're on the train ride, there's the official that walks up and down the aisles, that inspects all of your tickets and says, "Tickets, please," and then checks to see that you belong on the train. You can think of the natural killer cell as that conductor going through the body, checking everyone's ticket, making sure that they belong in the body. And there's 2 signals specifically that our natural killer cells will look for. If they don't get those 2 signals, the natural killer cells will activate and destroy that cell. The natural killer cell will go, hey, you don't belong here, and then destroy or initiate autolysis within that cell. And it'll initiate autolysis a couple different ways. It can release perforins. This is a category of protein that is going to create holes in the cell membrane. A key difference between the perforin and the membrane attack complex is that the membrane attack complexes come from proteins that are just circulating in the blood plasma as part of the complement cascade. These perforins are going to be specifically exocytized or released by the natural killer cell. So they come from two different locations, but they have remarkably similar structural and physiological responses. They make a hole, and the hole kills the cell. When we look at the other way that natural killer cells can destroy or trigger autolysis, they can do that by releasing granulozymes. And these granzymes, sometimes referred to as granulozymes, these are enzymes that are going to focus specifically on destroying proteins intracellularly. It's a way for the natural killer cell to digest its target cell from the inside out. It's kind of like how a starfish, when consuming its prey, it will release stomach acids and digest something and then swallow it after digesting. Same thing with spiders as well. They digest it, their insect, and then they eat their insect after digesting it. Our natural killer cells will use the perforin to poke a hole in the cell membrane and then insert granzymes or protein-destroying enzymes through the hole and cause the target cell to be digested from the inside out. So in addition to the hole just causing the cell to lose its chemical equilibriums, the hole also allows for another point of attack. Natural killer cells, when they're functioning properly, are amazing. They remove bacterial cells from our bodies, they remove virally infected human cells from our body, and they remove cells from large multicellular pathogens from our bodies as well. So they're super effective when they're operating correctly. However, they're a pain in the butt, particularly for transplant patients. If you receive a transplant from one person to another person, there is this category of signaling molecules called majohistocompatibility complexes, or MHCs. And these surface molecules help to differentiate the cells that belong in my body from the cell that belong in your bodies. So we can have a human red blood cell or a human skeletal muscle cell. And if it's from one person to another person, there's going to probably be very different surface markers. These surface markers are genetically related. So we find that siblings, or if there's any kind of a biological relation, there's a much higher chance that these surface marker proteins are the same, which is why we typically do donations preferentially, tissue donations or organ donations from between family members that are biologically related. When somebody receives an inappropriate transplant, the natural killer cells in the recipient's body will attack the cells of the transplanted organ or tissues, destroy it. I know I, in particular, have cadaver tendons inserted into my body. I tore my ACLs 3 times when I was in high school, and I didn't have any more patella ligaments to chop up to harvest. So for the 3rd surgery, they took an Achilles tendon from a cadaver and cooked it, some chemical cocktails, to remove all MHCs from those cells so that my body wouldn't reject that cadaver donation. Another issue with the natural killer cells that I find to be particularly chilling is during bone marrow transplants. Every once in a while, somebody with leukemia gets an inappropriate bone marrow transplant. And that bone marrow that they receive starts to make brand new leukocytes. It resets their immune system. And the brand new immune system that bone marrow recipient is receiving starts to make natural killer cells that destroy all of the other tissues in the patient's body. Thankfully, that's pretty rare. There's lots of genetic screenings done before bone marrow transplants are done because of the severity of that issue. But it does happen occasionally. So those are the natural killer cells. let's talk about fever. So when we think of fever, I just want you to think of being hot. It's an elevation of our body temperature. And like most things, a little bit is good, too much is bad. A slight elevation in our body temperature is actually pretty effective for fighting off some kind of disease state or a pathogen that's reproducing in our bodies. The bad thing is when the fever accelerates too much and we have too much of an elevation of our body temperature. So the baseline for our human body temperature is about 37 degrees Celsius. That's an average baseline. There's a little bit of fluctuation, either a half a degree up or down, depending on the individual's baseline. And during the fever state, we elevate baseline body temperature. We reset the thermostat inside of the hypothalamus of the brain. And we do that specifically because those mesophiles, or those bacteria that are preferentially reproducing in our bodies, they really like 37 degrees Celsius. But if we heat up to 38 degrees Celsius, the bacteria are outside of the optimal temperature range for their enzyme function, and they have a degraded metabolism, and it's easier for our body to fight off the bacterial infection. Now, when we look at a fever, it's associated with being hot. And most of the technical terminology associated with fever is going to have the word fire. That's pyro associated with it. Think of a pyromaniac, somebody who likes to make lots of fires. So when we have pyrexia, that's a technical name for fever. Another technical name you'll see every once in a while is febrile. So if there's a febrile seizure, which is something you'll probably hear about every once in a while, that's a seizure associated with somebody's body temperature being too high, or some kind of a secondary symptom associated with the high body temperature. Now, in addition to inhibiting the reproduction of bacteria and viruses within our bodies, we also find that the cells of our immune system actually have an optimal functioning temperature at about 38 degrees Celsius. So not only do the bacteria and viruses not work as well when we have our elevated body temperature, our white blood cells, our response system functions better at that slightly elevated temperature. So when we think of a drug that's designed to reduce the fever state, I want you to think of an antipyretic. The two, or probably the single most common antipyretic on the market is Tylenol, or also known as acetaminophen, there we go. Not acetylcholine. That's a neurotransmitter. That would be trippy, though, if you took an acetylcholine pill. So when we think of acetaminophen or Tylenol, it's a super common antipyretic. Other antipyretics on the market include aspirin or ibuprofen. And when we think of ibuprofen, that's in a category of drugs known as NSAID, or non-steroidal anti-inflammatory drugs. And all of these antipyretics function in basically the same way. They short-circuit the mechanism that causes us to elevate our body temperature. There's a specific kind of signaling molecule in our body that is involved with this process, known as a prostaglandin E sub 2, or E2. And these prostaglandins are made by two different enzymes. Acetaminophen targets, or Tylenol, targets both of the enzymes at the same time and has more side effects. This is why a lot of people will oftentimes have stomach pain associated with Tylenol, with some of those side effects because of its broader activity. Ibuprofen only targets one of the two enzymes associated with making the prostaglandin E2. Therefore, it has fewer side effects, and it's oftentimes not associated with that stomach irritation. Regardless, both of these drugs function as an anti-fever drug, or an antipyretic. Now, when we think of the fever state, the most common way we initiate the fever state is when we look at an exogenous pyrogen, or some kind of molecule from outside of our body that induces fever. A pyrogen is any molecule that induces the fever state or any molecule that elevates our baseline body temperature. Exogenous pyrogens are made from something out that doesn't belong in our bodies. I believe it's phospholipid A from gram-negative bacteria. Don't quote me on that. It's been a while. Some of the glycolipids on the surface of the bacteria that invade our bodies. As we destroy those bacteria, the bacteria self-destruct, and the cell fragments that are left over act as a pyrogen and initiate the cell response. Some other parts of the bacteria can act as a pyrogen. Sometimes bacteria will exocytize pyrogens. Some bacteria strains preferentially induce fever state, and we find that those bacterial strains are going to be transmitted through the bloodstream very rapidly when they induce that fever state. We also can have endogenous pyrogens. These are the ones that we make. So an endogenous pyrogen is a molecule we make that induces a fever. And these are typically going to be secreted by cells that attack and target the bacteria, those first responder cells. So the neutrophils and the macrophages. We also find that as we look at our fever, there's some classic stages of the fever as those pyrogens or those prostaglandins make it to the hypothalamus. And I'm going to say this again just to emphasize. The hypothalamus is the part of the brain with that set thermostat. All those pyrogens, all of those prostaglandins go to the hypothalamus, or it will trigger molecules to go to the hypothalamus to make our brain increase our body temperature. During these stages of the fever, and this is just the normal course of a generic fever, we're going to have that dynamic equilibrium. Our body temperature keeps going up and down just a little bit over a set baseline. So it's getting cold outside. You might shiver a little bit when you're outside, and then you come inside and you're wearing a sweater because it was cold outside, and now you're too warm, and now you might be a little bit sweaty after sitting in this lecture hall for a little bit. That accounts for those normal fluctuations in our body temperature. However, if we have pyrogens being secreted into our bodies, either endogenous or exogenous pyrogens, those pyrogens travel to the hypothalamus and cause the hypothalamus in our brain to increase the baseline temperature. This is known as onset, when we have the temperature rising. And then our temperature will rise to a specific set point. For most fevers, they typically, to use Fahrenheit, will go to 99 or 100, or every once in a while 101 degrees Fahrenheit. And most fevers aren't that significant, and they resolve themselves pretty rapidly. Maybe you'll pop a few aspirin or Tylenol to help manage the symptoms and help you feel more comfortable. Every once in a while, though, that set point will be raised to 39 degrees Celsius or 102 Fahrenheit, 103 Fahrenheit, and that's typically when we need to have medical intervention. During this stadium phase, or the steady state phase, our homeostatic balance, or the dynamic equilibrium, is set to a higher temperature. And then once our infection has ended, our pyrogens are no longer being sent to the hypothalamus, and there's a little bit of lag time. It takes a little bit of time for the hypothalamus to respond to the lack of pyrogens and reset the thermostat to the baseline. And that gives us the last phase, the deferescence, when we have our body temperature returning back to normal. Another response is the inflammatory stage, or inflammation. When we think of inflammation, inflammation should be a localized response. And when it's functioning properly, it is always a localized response. Occasionally, we can have an allergic reaction or some kind of malfunction of our immune system that can trigger body-wide inflammation. That's a big problem. But when we have inflammation at the site of injury or the site of infection, it's actually quite beneficial to our bodies. And like most things, there's some give and take. I know we have a lot of kinesiology majors in here or aspiring physical therapists in this room. And lots of physical therapists will spend time working with joint repairs or joint replacements, arthroplasties. And there's a little bit of give and take where you want a little bit of inflammation to help promote the healing process. But if there's too much inflammation, that can inhibit blood flow and inhibit the healing process. So you'll learn more about that in your specific classes about how to manage that response. But generally speaking, as we look at inflammation, it makes it difficult for pathogens to spread. It's going to help increase circulatory response and remove damage and debris from our tissue. And it's also going to accelerate tissue repair when it's working appropriately. As we look at the stages of inflammation, those stages include redness, swelling, heat, and pain. Now, when we look at inflammation, most of you know this off the top of your heads because I've talked about it a lot last semester, but the suffix itis, I-T-I-S, is a suffix that we use to say inflammation. So if we have arthritis, that's an inflammation of an arthritic joint or a movable joint in our bodies. If we have bursitis, it's inflammation of the bursa in our bodies. So if you take that itis suffix and tag it onto a root word, that could mean inflammation of that particular part of the body. A lot of people in my occupation will get laryngitis after teaching summer school and lecturing for 7 to 8 hours straight. You'll go home and you won't be able to talk. You have inflammation of your vocal cords. Now, during this inflammation response, there's a chemical that initiates inflammation called a cytokine. These cytokines are going to be released by the white blood cells or leukocytes and alter the physiology of those receiving cells. Most of those receiving cells are going to be cells associated with the blood vessels because our inflammatory response is so closely linked to the performance of our blood vessels. And these cytokines are very short range, and that's a good thing. Because the cytokines are short range, will trigger the inflammatory response in a localized area of infection or damage, and we won't have systemic inflammation from the cytokines. So because they're short range, they're categorized as a paracrine, and because they can act both on the neighboring cells and the cell that secreted them, they are also categorized as an autocrine. So when we think of endocrine, and this is just some terminology we're clarifying, an endocrine molecule is sent to the bloodstream and will affect other tissues far away in the body. A paracrine molecule will only affect neighboring tissues in the body, and an autocrine molecule will affect the cell that secreted it. As we look at the cytokines, there's a lot of chemicals in this umbrella term. Some of those chemicals under the umbrella include the interferons and interleukins we've talked about. Another one, known as tumor necrosis factor, is a specific kind of cytokine that helps to destroy cancerous tissues in our bodies. I don't want you to spend a lot of time learning about the different kinds of cytokines. I want you to internalize that cytokines produce inflammation. It's the big take-home from this slide. Cytokines are molecules that cause inflammation. So as we look at a typical inflammatory response, I can't help but think of my mom. She's such a worrywart when it comes to her children. And she would always say, is it infected? Is it infected? Is there redness? Is there swelling? Does it hurt to touch? And then she would poke me where I had my owie to see if I would say, cry out in pain. These cardinal signs of inflammation are usually going to be associated with a site of infection as well, because inflammation is the response to infection. So when we look at this, if we have increased blood flow, or actually let's think of it this way. If we have vasodilation from the cytokines, vasodilation causes the blood capillaries to open up wider and become more leaky as we vasodilate those capillaries. So if we cause the blood vessels to become wider, we're going to have more blood delivered to the tissue. More blood means heat from the core of our body. As we cause those blood vessels to become dilated, we have more red blood cells. Red blood cells are red, so we'll have some redness associated with inflammation. As we swell or dilate the blood capillaries, will have more blood plasma leak out into the interstitial or extracellular space. And that causes there to be fluid buildup in that area and swelling consequently. And then finally, as we have this process of swelling, a lot of times we're going to pinch nerves. We can cause minor impingement of our nocioreceptors or pain receptors associated with the swelling. And that can lead to elevated pain. But these cytokines also are going to prime our pain receptors to be more responsive to pain. And it's a good thing. Pain can be beneficial. There's a whole category of diseases associated without feeling pain. Advanced type 2 diabetes or diabetic patients can't feel pain in the extremities of their bodies, their hands or their feet, and will oftentimes accumulate lots of little bits of tissue damage. They don't feel the damage, they don't feel the inflammation, they continually have all of these little injuries building up until they have gangrene set in. They can never heal from the injuries, and they end up having their extremities amputated. Another classic one is it's an ancient disease associated with the skin turning white. Leprosy, there we go. Lepers are also associated with not having that pain response. And because they don't have that pain response, they continually damage tissues and start to have infections set in and have parts of the body fall off. So the pain is a very good thing. This pain keeps us from injuring our tissues after they're damaged and gives us time to heal from the injury. Another aspect of inflammation is that we recruit lots of neutrophils. Those signaling molecules, in addition to triggering inflammation, are also going to recruit more phagocytotically active cells to the site of infection. So let's say you get a splinter or you get stabbed by something. You will have lots of bacteria injected into your body for every time you have your skin perforated, just because of how many bacterial cells we have. One of my favorite statistics is for 10 to 1. Every human cell in our body corresponds to 10 bacterial cells in us or on us. And that's the normal healthy state for our microbiome. So once we have that damage to our skin, we will have bacteria entering our bodies. And in response to those cytokines or signaling molecules, we're going to recruit neutrophils to the site of infection. There's some key steps that have to happen. First, the neutrophils are kind of like the cop car on patrol. And that cop car on patrol needs to know when to turn onto the side street to get to the site of the disturbance. And our turn signal, so to speak, the thing that causes the neutrophil to leave the blood vessel and go to the site of infection, is this process known as margination. In response to cytokines, the endothelial cells of blood capillaries are going to release proteins that recruit neutrophils. And as the neutrophils are randomly bouncing through our blood capillaries, they'll bounce into these surface signaling proteins and be triggered to exit the bloodstream. The process of exiting the bloodstream is known as diapedesis, or the 2-foot process. During this process, during diapedesis, the neutrophil will extend a pseudopod, or a false foot, through the lining of the blood capillary, in between the cells. Because the neutrophil effectively is breaking itself into 2 globs, as it's squeezing through this little tiny crack, it looks like it has 2 feet, hence the name diapedesis, for this process of squeezing through the blood capillary lining. And then after the neutrophil exits the blood capillaries and gets into the tissue itself, there's this process known as chemotaxis. During chemotaxis, we get a positive and negative chemotaxis. It's this process of a molecule either moving closer to a chemical signal or moving farther away from a chemical signal. In this case, cytokines trigger positive chemotaxis. Neutrophils are going to move towards increasing concentrations of cytokines and go to the site of injury. The two particular cytokines in this situation that trigger chemotaxis are the bradykinin and the leukotrienes. So let's start focusing on the really interesting stuff. We focused on our broad aspects of our immune system. We focused on our lymphatic system. Let's start focusing on the specific or the adaptive immune system. This is where things get particularly interesting. So let's refresh a little bit from last class period. As we look at our material from last class period, our immune system isn't actually an organ system. The lymphatic system is the organ system. The immune system is just a bunch of loosely associated cells working together for a common purpose, to fight off infection or remove pathogens from our bodies. Now, when we look at our immune system, particularly the adaptive immune system, it's distinguished from the innate or non-specific immune system three primary ways. The biggest, the most important way is specificity, which is why that was the word that I omitted from the student version of the PowerPoint. Our adaptive immune system will only affect one specific pathogen at a time. This is the primary reason why every year there's a new flu shot, because the influenza virus keeps playing mix and match with its H proteins and M proteins to change up how it appears to our immune system. So our immune system needs to constantly develop a new specific immune response to that new variation of the influenza virus. This is also a reason why a lot of us won't develop a second infection after we've had an infection. And actually you're of the age, probably had the chickenpox vaccine. If you're born before the 1990s, there was no chickenpox vaccine. You had to develop an infection away and be exposed to the pathogen. And what we find is that in addition to having a specific response to a specific pathogen, we also have the all-important immune memory. And this is the reason. This immune memory is the reason why we aren't all always getting constantly sick. Sometime in the next 10 years, most of you in this room are going to become parents, just based on the demographics. And you'll find with your children or future children that there are two key stages where they're constantly sick in their lives. The first key stage is when you stop breastfeeding them. And then they all of a sudden are sick for a month straight. The other stage in a child's life when they're sick constantly is that first time you send them away to be with a bunch of little kids. Either you send them to daycare, or you send them to elementary school, or you send them to high school, that first time they go off to school. So I sent my first two kids to daycare, and they were healthy, started going to daycare, were disgustingly sick for a month or two. I had some friends who were homeschooled throughout elementary school and middle school, and as a homeschool student, they didn't have that much interaction with other individuals, and then they went to high school, and they were exposed to the cesspool. And they were sick forever, for a month straight. We also find this during family reunions. One of the reasons why we're constantly sick around the holidays is because we're exposing ourselves to people from far away that have novel pathogens that we don't have immune memory to. And then finally, it's worth mentioning, there's the systemic effect. Our specific or adaptive immune system is going to act body-wide. So within our adaptive or specific immune system, we have cell-mediated immunity and humoral immunity. And this word for humoral immunity, this is one of those really old school terms that's just become embedded in the literature. Back in the 1600s, 1500s, back in the mid-second millennia, there was the theory of the four humors, where you had the four liquids of the body, blood, bile, saliva, and urine, and you had to have the correct ratio of those liquids to be healthy. That field of medicine is represented here when we say humoral immunity, immunity associated with the blood. So in modern medicine, when we say humoral, we mean blood. And when we think of our cell-mediated immunity, this is typically going to be the focus of intracellular pathogens. Intracellular pathogens. Or more broadly speaking, for cellular immunity, I want you to think viruses. For humoral immunity, I want you to think bacteria. And this is a broad brush stroke. We can destroy viruses while they're in the bloodstream, extracellular, and some bacteria will be intracellular bacteria, but generally speaking, most viruses are intracellular, most bacteria are extracellular. So let's talk about our cell-mediated or cellular immunity. This is going to be modulated by lymphocytes, in particular our natural killer cells and our T lymphocytes. And we're going to find cells that have an intracellular infection and destroy that cell. And the idea behind this is the needs of the many outweigh the needs of the few, to quote Spock. So the idea behind this is it's better for us as a whole if we destroy a couple of our cells while they're infected, as opposed to letting that infected cell live and infect other neighboring cells while the pathogen reproduces inside of the infected cell. When we look at this process, these pathogens that are intracellular or inside of human cells are particularly hard to get to because they're hiding inside of a cell, inside of our bodies. And our body's immune system, if it's fully immune competent, is designed to not destroy the cells that we make. We design our immune system not to destroy our own human cells. So these pathogens that hide inside of our own human cells are very difficult. Antibody responses, which we'll talk about probably on Tuesday, don't affect these intracellular pathogens. Antibodies can circulate through the bloodstream and the other extracellular fluids, but antibodies don't affect something while they're hiding inside of our own human cells. So when we think of the blood or humoral immunity, another name for this is going to be antibody-mediated immunity. These are extracellular pathogens, and these extracellular pathogens are available for targeting by the antibodies. As we look at this process, we can have different antibodies in our bodies. Breast milk versus saliva versus mucus versus blood. These different fluid compartments or liquids within our bodies will have different variations of antibodies. Mostly, though, when we think of humoral immunity, we think of the blood-based immunity because these antibodies will travel through the bloodstream to get to their tissue compartment. As we look at our adaptive immune system, there's 4 variations of it. We can have natural and artificial, and active and passive. So when we think of a natural active immunity, this is you making antibodies in response to getting sick the old-fashioned way. I have natural active immunity to the chickenpox virus, or I believe herpes zoster is the technical name for that one. So I've been exposed to chickenpox. I had to develop my own immune response, and now my own antibodies. Most individuals in college now have never had chickenpox. They were given a vaccine for chickenpox. They have artificial active immunity. Instead of contracting the disease the old-fashioned way, they were given some of the antigens of that diseased or pathogen, and they didn't develop the disease state, but they did develop the immune response. So individuals that have the vaccine will have those weakened or non-functional pathogens trigger the immune response, and then they'll start making antibodies in response. Every once in a while, we need a booster shot for our vaccines. Some vaccines are able to have long immune memory associated with them. Other pathogens for other vaccines have short immune memory associated with them. Something unique happened to me 2 weeks ago. This is the first time this has ever happened to me when I went to the doctor's office. I was visiting with my family physician, and I said, hey, I want my flu shot. I can't get sick because I can't cancel lab. Yeah, I will, if I ever cancel lab, it's because I'm, for the record. And she looked at me and she said, well, I want you to wait. I don't want you to get your vaccine right now. And I was kind of taken aback by that because I'm so used to the physicians being like, please get your vaccine. No, really, please get vaccinated. Please. And the reason she said, please wait, is the influenza vaccine has a short lifespan of 4 to 6 months for primary efficacy. After 4 to 6 months, those influenza vaccines that we get start to lose their effectiveness, which is one of the reasons why every year, in addition to new strains of the influenza vaccine, we also get a new vaccine that acts as a booster shot as well. I know in the town I live in, River Falls, everyone got vaccinated last September of 2018, and they were fine through the fall semester. And then April of 2019, they had 30% of the elementary school students reporting an absent because there was influenza outbreaks after that shot had lost its efficacy. So my plan right now is, for the record, I got vaccinated, and I'm going to get revaccinated in January. We also have natural passive immunity. When we think of natural passive immunity, this is when you naturally are getting somebody else's antibodies into your bloodstream. The best example of this is breastfeeding. Breast milk from mom to child contains a lot of antibodies. Child consumes those antibodies and will have passive immunity to whatever the mom is being actively exposed to at that point in time. Another way we can have natural passive immunity is as antibodies travel across the blood-placenta barrier. We talked during transfusion reactions, particularly when mom is Rh negative and the baby is Rh positive. We talked about how antibodies can cross that barrier. Most of the antibodies that cross that barrier are good for the child growing in the womb. Occasionally, in those blood typing situations, they aren't so good. And then we have artificial passive immunity. This is when you're injected with a concentrated shot filled with antibodies. Artificial passive immunity is when somebody is injecting antibodies into your body. This most often is going to happen when you're given antivenom or antitoxin. An antivenom or an antitoxin is going to be an antibody designed to neutralize whatever that particular large macromolecule is, to keep it from triggering an immune response. Let's talk about antigens. We've been talking about antibodies. An antigen is any molecule that can trigger an immune response. It's worth emphasizing that antigens are large. Little tiny molecules by themselves cannot trigger the immune response. But if it's a big, fat molecule, typically with a molecular weight of over 10,000 AMU, it's capable of triggering an immune response. Another way to think of an antigen is it's a molecule that an antibody can bind to. It's big enough to be targeted by an antibody. Now, as we look at these antigens, most of the antigens in our bodies are good antigens. They are, quote unquote, self-antigens. They're an ID tag that lets the cells of our bodies know that whatever cell type we're looking at belongs. So if we go back to the natural killer cells, well, the natural killer cells patrolling the tissues of our bodies, it's looking for self-antigens to be expressed on those cells of our bodies, our own self cells. As we look at an epitope is just a variation of an antigen, or it's a different part of an antigen that the antibody could bind to. Some antigens are so large that different antibodies can bind to different parts of those antigens. To go back to the influenza virus, current vaccines for the influenza virus focus on the N protein, the neuradenamase protein on its surface, and then the H protein, whose name eludes me right now. But there's a third protein that's constant throughout all influenza viruses that we're currently trying to develop a vaccine for. So we could have one vaccine to cover all strains for good. That third protein is a third epitope on the surface of the influenza virus. And then we have haptens. As we look at haptens, a hapten is a molecule that cannot trigger an immune response by itself, but when it binds to a larger molecule, it can work with that larger molecule to trigger an immune response. Include molecules that we're allergic to. So typical antibiotic medication will have a molecular weight of less than 10,000 AMU, and all by itself cannot trigger the immune response. However, when that antibiotic molecule binds to a larger molecule within our body, they combine to form something that triggers the immune response. So to reiterate this, as we look at haptens, a hapten by itself doesn't trigger the immune response, but inside of our bodies, the haptens attach to larger molecules and work together to trigger the immune response. And when you're done with this question, we'll be done with our presentation today. We have haptens, antigens, and pathogens. Which is which? They all sound kind of similar to each other. So let's make sure we can differentiate them from each other. We're down to 30 seconds. Oh, okay. Just hit submit.
Yeah, that's
perfect. Yep.
couldn't answer the question or do
Okay.
penance.
That's